Now we will pass it to a extractive distillation column, okay, where NMP will be given. So this is the identity of the extractive distillation column. So we will pick up a rat frag column from here, and we will connect this destination, and we will have another material input over here, that is NMP. Okay. Now it is said that NMP on the 5th stage and feed enters on the 17th stage. So in order to make it visually correct, we will take it over here, and this one we will connect it over here. Okay. So let us pull it to some extent. Yeah. So this is the dist 1 or dist call 1. And this is NMP. And what are the outlets? It is partial vapor liquid. So we have both vapor outlet and liquid distillate outlet. And obviously we will have some bottom product as well. We will call them vent because it is vapor. And this one we will call dist 1, distillate 1. And this one we will call bottom 1. Okay. Now we have to specify NMP. Now NMP, it is given 500 kilomole per hour. So this is 500 kilomole per hour. And temperature pressure is given 93 and 1.4 bar. So 93 and 1.4 bar over here. So NMP is specified. Now we have to specify the distillation column. Now distillation column, extractive distillation column, it has 22 theoretical stages with a partial vapor and liquid condenser. So it is partial vapor liquid condenser. The feed enters 17th stage, NMP 5th stage. So feed enters 17th stage and NMP at 5th stage. Both are on stage. Okay. Both are on stage. In the configuration, distillate rate and reflux ratio, you might remember that distillate rate and reflux ratio are clubbed with recovery and purity of N-heptane. So we have to use some kind of design spec over there. But to begin with, the initial gas has been given, which is 40 kilomole per hour and 3 respectively. So we write over here as 40 and 3. And then the pressure, the condenser pressure has been given. It is atmospheric pressure. So it is 1 atmosphere and condenser is 94 degrees centigrade. So it is 94. Okay. So that way the distillation column 1 is fixed. Now the outlet of this distillation column, the bottom product of this distillation column, it is fed to a second column, which is NMP generation column. So we need another rad frag column over here, and we will connect this one over here. Okay, and this is a total condenser, so there will be no vent and total liquid outlet. So here we will name them as dist call 2, this one is dist 1, sorry, this is dist 2, and this is bottom 2. Okay, so that way we are fixing the distillation column, and obviously we have to specify the distillation column, which has 12 stages. Condenser is total, and again the distillate rate and reflux ratio, we have to use a design spec to club with recovery and purity, but initial guess 40 and 3 respectively. So we give 40 and 3 over here, and the streams, the feed enters at 6 stage, so we'll write 6 over here on stage. Pressure, the condenser pressure is atmospheric, so we'll write 1 atmosphere. That makes our work simpler. Okay, again we can run it. Yeah, so results are available, but our job is not complete because we have to perform this design spec. Okay, now let us check. We will take the flow sheeting option. Here design spec is there. So first design spec, let us write DS11. We will define the purity, and the purity is a stream variable, which is the mole fraction of N-heptane in distillate 1, right? So N-heptane purity. So mole fraction of distillate 1, the component is heptane. And we shall spec this purity to be 0.99 with a tolerance of 0.0001. Okay, and what will vary? Will vary the distillate rate. So we will vary it, the block variable of distillation column 1 and the mole D. So this is the total distillate molar flow rate. So we are clubbing distillate rate with that. Now what is the distillate rate? Normally it is 40. Let us take a lower limit of 35 and upper limit of say 60, and let us check what happens with that. Okay, now run this system once again. Yeah, check the results. So it finds at 44.2166. Okay, so actually with a 40 kilomole per hour of distillate rate, we are getting 99.96, which is far more than 99%. But the thing is, we do not need that much of purity. 99% is enough for us. So with 44.2166, this is okay with us. Now, in the same manner, let us take the conversion component also, recovery. So there we write recovery. We have to define it as a local variable. Okay, it's a local parameter for us. So what is the recovery? Recovery means the amount of heptane that is recovered through the distillate over the amount of heptane that has come through the feed line. That has come as a feed to the distillation column 1. So that is our recovery. So we will use that recovery as a local parameter. We'll define a few more things. One thing is that distillate heptane, which is a stream variable, and this is the molar flow rate of dist 1, and component is heptane. Okay, so this is dist hep. And another thing that we will define as the feed hep. Okay, and what is feed hep? Feed hep is also a stream variable, and this is also a molar flow of the reactor in, not reactor in. Actually, it is the stream that is going into the distillate 1, the distillation column 1. So, what is going in through the distillation column 1? It is dist 1 in. So, we will take it as dist 1 in heptane. Okay. So, whatever heptane that is coming through feed and whatever heptane that is going out through the distillate, ratio of that is the recovery. Okay. Now we will define the Fortran code as recovery is equal to dist 1 or dist hep. I think it is dist hep, right? Let us check. Dist hep by feed hep. So dist hep by feed hep. And recovery should be 0.99 with this tolerance. So both of them are 99%. What we need to vary? We need to vary the reflux ratio. Okay. So reflux ratio is also a block variable. Which block? It is distillation column 1. Variable is reflux ratio. So reflux ratio will be this one, specified molar reflux ratio. Okay. And it should vary. Let us give a wide limit. So it is 0.5 to say 10. Let us see where it comes. Okay, within this range. Run it. Yeah. Now you check the results. Yeah, so it has come at 8.48349. At that point it has come. Okay. At that point, the recovery is 99% with some amount of tolerance. So that way, we are fixing the recovery and purity of N-heptane in the distillate of the distillation column 1. Okay. Similarly, we have to do the same thing with NMP recovery and purity. So let us do. Okay. So here we define purity as a stream variable of mole fraction of stream bottom 2 of NMP, right? Because NMP is going through the bottom. Okay. So NMP in the bottom stream purity, and this purity should be 0.998. This is 99.8, right? With a tolerance of, say, same tolerance you give. And what do we need to vary? We need to vary the distillate rate. So we have block variable of distillation column 2, and the distillate rate should be somewhere over here. Distillate molar flow rate. Okay. And here also it is 40 kilomole per hour. We can give within this 35 to 60 range. Let us see what happens. There is a problem over here, so results are not coming as expected. So, okay. So we have done a mistake. We should not use mole flow, right? It is mole fraction. Mole fraction of the NMP. That is the purity. Mole flow is not the purity, right? So with this mistake, we were not getting the solution. Now let us run it. Yeah, now we are getting a solution, and let us check the results. Yeah, so with 40, we were getting at 98.8, whereas at 44, we are getting at 99.8. Okay, so this is the result. So similarly, you can do the other design spec also. Take it as a practice lesson for yourself and try it yourself. I am not doing it over here. Now we continue the problem in the next page. Now we will do this methane combustion later. First, let us understand what we have achieved so far. So this is our total structure. So what is the duty, heat duty? It is 2123 kilowatt, almost 2.1 megawatt. What is the heat duty of reactor? This is also 5.1 megawatt. And cooler, we are losing heat 3.8 megawatt. Okay, so obviously we can use some amount of heat to preheat this one, right? So we'll explore it later. Now let us check other one. This is another heater that we have. What is the heat duty? Oh, it's not that much. It is 329 kilowatt. Okay, whatever it is. Actually, it is increasing the temperature from 25 degree to 93 degree centigrade. So the heat duty is not much. But here the heat duty is quite high, because 25 degree to 427 degree centigrade. And then again back to 25 degrees centigrade. So the change is quite high over here. Anyway, now let us go to the next portion of our work, that is the combustion. Okay. Now in the combustion reaction, we have air and methane that will react in a stoichiometric reactor. Okay, so let us take up a reactor, stoichiometric reactor, and there will be two material in. One is air and there will be another one which is methane, and the outlet temperature of the flue gas will be cooled to 550 degrees centigrade. So there will be a cooler over here. So let us use a cooler and connect them. Okay. So let us rename them first. This is our air. This is methane. This is our reactor output or react to output. This is our combustor. And this is the second cooler that we have. So we have cooler 2. And this is the flue gas. Right? This is our flue gas. Now we have to specify air. Air temperature and pressure 25 degrees centigrade and 1 bar. So it is 25 degrees centigrade and 1.5 bar rather. So it is 1.5 bar. And the flow rate. Now here it is an interesting thing is there. The flow rate of air should be 10 times that of methane in order to ensure 100% conversion. And what is the methane flow rate? The methane flow rate should be such that the outlet temperature of the flue gas is 550 degrees centigrade. So methane flow rate itself we do not know. How can we give a figure for air flow rate? And there we have to use a calculator block. Now for the time being, we give a small dummy figure over here. And that flow rate is say 1. But we have to provide the air composition. So mole fraction of air will be 21% oxygen. Carbon dioxide will be 0.04%. This is 0.04%. And rest nitrogen. So nitrogen will be 0.7, it is 7,896. Yeah. Now it is done. So total mole fraction is 1. Now I have given a dummy variable, but we have to use a calculator block where the flow rate of air should be specified as 10 times of the flow rate of methane. Now methane, again, the initial gas is 80 kilomole per hour. So methane is 80 kilomole per hour. Temperature and pressure has been given 25 and 1.5 bar. So this is methane. And we have to specify the stoichiometric reactor condition, runs on atmospheric pressure and -1 megawatt of heat duty. So we do not have temperature, rather we have heat duty. And atmospheric pressure, so 1 atmosphere pressure, and heat duty is 1 megawatt, right? So it is -1 megawatt rather. Now go to the reactions. Reactions, you have new reaction, which is CH4 plus oxygen, 1:2 ratio, which yields carbon dioxide and water. So carbon dioxide and water also in 1:2 ratio. And the conversion is 100% because we are providing excess air in order to ensure the 100% conversion. So this block is done. And cooler. So the cooler temperature, the methane flow rate should be such that the outlet temperature of the flue gas is cooled to 550 degrees centigrade. Now, again, we have to use a 0 bar pressure because there is no change in pressure over there. And again, we have to perform some design spec analysis over there. But for the time being, let us specify the temperature over here as 550 degrees centigrade, run the system and check it first. So run the process. Okay, so there are some errors. Let us see what are the errors. It says component OT has 0 flow rate. So let us see what problem is there. Okay, I understand what it is. We have not given the required flow rate of air. We have given only 1 kilomole per hour. Okay, so enough oxygen is not there. We have forgotten over here to add a calculator block because you saw this option, right? You saw this option. It says that flow rate of air should be 10 times that of methane. So that we have to ensure. So here we take a calculator block. Then define NMH4, sorry, NCH4 rather, and that is stream variable. The stream variable of CH4 molar flow rate. Similarly, we have N air, that is also a stream variable of air stream variable rather, not vector, air and mole flow rate. Okay, now this one will be import variable and this one will be export variable, and we'll calculate through Fortran command, N air is equal to 10 times that of NCH4. Okay. So that gives the information to Aspen Plus that the flow rate of air should be 10 times of that of the methane. Okay. Now let us run it once again. I hope there is no problem. Yeah, there is no problem at all. So we are running two parallel systems. One is this one, another is this one. So here we have seen let us click the heat work power. Okay, you see how much heat is there. Now if we make it to SI unit, so this is in watt. Now you can see what is the wattage over there. This much of watt. So 2.1 megawatt, 5.1 megawatt, 3.88 megawatt negative, this negative sign, right? This is not much. Here you see the reboiler heater is 6.7 megawatt and here reboiler is 2.11 megawatt. On the other hand, here we are taking out 1 megawatt from here, still 40 megawatt heat is over here. Okay. And the temperature is up to 823. Okay. We are specifying the temperature at, okay, it is not degree centigrade, it is in Kelvin. So in degree centigrade is 550. So we are running two parallel processes. We have not done the heat integration. So the first question that it was asked, calculate the amount of methane required without process heat integration. So we have to use another design spec. So what should be the value of methane over here for which the temperature will be 550 degrees centigrade? So that work we need to do.